Welcome to the review of the OWON P4305 linear power supply. 0 to 30 volts, 0 to 5 amps, 150 watts. This will probably a two-parter. In this part 1 I want to cover the basics, so what's in the box, have a look around the unit, basic operations, and the electrical qualities, so noise, regulation speed, etc. In the second part I will talk about the user interface and the options in detail. Remote control, this has a serial interface, and we'll have a look under the hood. So let's start with what's in the box, and if you haven't seen it, there's an unboxing video, card link. Besides the unit, you get a 15-page printed manual which covers about everything, a two-sided technical specification sheet, a 140 centimeter 9-pin sub-D serial cable, a 150 centimeter mains AC cable, and a spare fuse, 220 volts, 3 amps. The unit itself is 19.5 centimeter high, including the handle stuff here. Has a width of approximately 11.5 centimeter, and if I take the binding posts into account, about, in depth 29 centimeters. It weighs in at 6 kilograms, so 13 pounds, and that's why we have this really sturdy handle here on top. At the back you'll find your standard IEC mains AC connector with an integrated fuse holder, initially covered up by a very sticky warning sticker stating the voltage the unit is designed for, your RS232 connector for remote control, and the opening for the cooling fan. Both sides are slotted to allow for cooling airflow, so don't get the idea that you can stack these side by side. They probably will overheat. The rubber feet on the bottom are very big and sturdy and screwed on. That's nice. The front sports a big LCD display, the usual stuff of a lab power supply, and a real power on-off switch. That's not standby, that's really hard power on-off. And the boot up time is pretty short, you barely notice it. You can read the display from 45 degrees above without a problem. 45 degrees from below is also no problem. 45 degrees from either side is not great, but still okay. So let's start with a basic operation. The display shows you that it's an OWON, waste of space because there's an OWON logo right below here. If the output is on or off, that's really nice. And if the internal loudspeaker, which is really just a piezo beeper, I guess, is on or off. You see the actual output voltage, the actual output current, and the actual output power with, 3 decimals. And you also get displayed if the unit is operating in constant voltage or constant current mode. You have here your set voltage and your set current, and even smaller, your over voltage protection and your over current protection settings. And at the bottom you get a little help, how to operate the unit. For basic operations you just need the mains AC on-off switch, the cursor keys, the rotary encoder here which is indented, and the output on-off switch. That's it. With the cursor keys up down you select which parameter you want to set, so over current protection, over voltage protection, output current or output voltage, and with left right you select the digit you want to change or can change with the rotary encoder. So if I want to go to 5 volts, I can do this right here. And yeah, there's an overflow to the left if you turn this up. Yeah, output on off, I don't need to explain that. If you turn the output on, you get an output voltage and current, of course. Note that if you change the voltage here, the unit takes some time to adjust the output. So if you change it really slow, the unit will follow you with maybe less than half a second delay. But if you change it really quick, it takes a while. Okay, keep that in mind. And that's it for basic operation. One reason to buy a linear power supply like that one is that you want really low ripple and noise at the output. And OWON promises you in the spec sheet less than 4 millivolts peak to peak, respectively less than 1 millivolt RMS ripple and noise between 20 Hz and 20 megahertz. And it's really hard to measure these millivolt ripple and noises without any specialized equipment like differential one-to-one probes with 20 megahertz bandwidth for a few $1,000. Yeah, I put a link in the description to EEVblog's video about measuring ripple and noise of power supplies. The best I can do currently, and everything is switched off, is about 7 to 8 millivolts noise level. Yeah, not from the power supply, just basic noise level. So, my probe is AC coupled. I have the bandwidth limit at 20 megahertz in. I'm using a one-to-one probe. That's good enough for the 20 megahertz. And I initially thought I could measure down to 0.5 millivolts with a one-to-one probe. Yeah, it didn't work out that way. 2 millivolts per division now, giving us between 7 and 8 millivolts peak to peak. Yeah, base noise without the unit even switched on. And timescale, if you can see here, the 5100 Hertz noise, 10 milliseconds, of course. To achieve this, I fumbled around about 2 or 3 hours. Yeah, I broke out my good test tech probes. Yeah, card link to the mailbag, and the tip of the probe is directly at the positive binding post here. I kept the ground connection of the probe as short as possible. Yeah, you can forget about using a hook and a ground strap. That doesn't work. You can also forget about using normal banana plug cable for your load. I constructed here a coax cable connection, and yeah, the ground branches off here, but the shielding continues here up to the positive binding post. And funnily enough, putting this yellow cable in here and basically connecting the frame of my load to ground helped also. What also helped was removing any 220 volts mains AC cables from the desk and putting them all on the ground. Okay, but it's not enough probably to see the noise generated by the power supply itself. But let's try. I found another unused but connected mains AC cable here somewhere in the corner and removed that. And now our noise level is down to 5 to 6 millivolts peak to peak. So let's see. And you see, if I put my hand here, you see how delicate that whole setup is. Or if I touch here. Yeah. So let's switch the power supply on and see if we can see a change. Well, certainly not in the level of the noise. I won't zoom in here, but yeah, it went up maybe a millivolt, but that's not the output. So let's switch on the output. needs a while to recover because we have AC coupling. And I removed my hand. And yeah, the noise is a little bit different, but yeah, peak to peak, 6, 7, and now we have 7, 8, okay, with about an amp of load at 24 volts. So, and you see if I put my hand there, it goes up. So let's go for full load here. And now we have between 8 and 9 millivolts. Let's say between 9 and 10 millivolts peak to peak. So yeah, the noise amplitude increased, yeah, from my base level of 6 millivolts to about, from 6, 7 millivolts to 10 millivolts. Okay, so an increase of, or added noise of maybe 3 millivolts. But yeah, that's as far as I can measure it. And it seems pretty much to be within the specs given for millivolts peak to peak. Okay, let's move on to greener pastures. This year doesn't start well for me. First, the problem with the Max 31855K, and now it seems the LCD of the OWON here is dead as a dodo. You see here some stripes, and I can cycle the power. And it's back. Okay, but we have to have a look at what's going on there. So, yeah, keep that in mind. Anyway, I wanted to capture some transients, and the first transient is, of course, yeah, switching the input on and off. That is, switching it on. And I have here my non-electronic load, by the way, card link, at full power. And these are, keep in mind, halogen light bulbs. So when they are cold, they have a much lower resistance than when they are hot. So we're putting really a strain on that thing here. So let me set up the oscilloscope to capture that switch on transient. Okay, switching on, and yeah, there it is. Let's have a closer look, and yeah, I will switch the output off here again, because you probably hear it at high loads, yeah, beyond 100 watts. This thing is really noisy. That is the fan in the back. So it comes on with a little peak and then ramps up really slowly. We have here 50 milliseconds per division, so that's 100, 200, 275 milliseconds, a quarter of a second, until it's up to the full voltage, and there's a little blip here. Let me zoom in and we measure how big that little overshoot here is. That overshoot measures in at 500 millivolts, so 2% of our total 24 volts. Let's try that with less current at 12 volts. Yeah, you're hearing the fan again, and I configured my load here, so we are drawing about 4.4, 4.3 amps, and there it is. Let's zoom in. So it's the same pattern at 12 volt, about-ish 50 watts. We have this little spike here, and then a wee bit of an overshoot until we reach the 12 volts. Let's have a closer look at the overshoot. This time the overshoot is 360 millivolts, so exactly 3% of our target voltage. Let's try that one more time at 5 volts. So set voltage 5 volts, about 3.5 amps load. And there we have the capture, and I can say there, the overshoot is getting bigger, but let's have a closer look. Definitely the same pattern, yeah, the spike here, and then the slow rise, and then the overshoot. Let's zoom in. Well, 280 millivolts. That's actually 5.6% of the 5 volts. Okay, one last time with a lower load, because this is above 5 volt of our target voltage. That's a bit, yeah, 5.6% of our target voltage. That's a little bit much. I'm gunning now for 5 volt at half an amp, and oh, that looks different, doesn't it? Now, that's the picture I would show in my spec sheet as a manufacturer. Of course, yeah, we are now only drawing about 2 watts out of the unit, so not very much. But then you get a really nice switch on transient. I would say a perfect switch on transient. However, keep in mind under high loads, 2-3%, or at the extreme 5.6% overshoot, okay? Just for funsies, the switch off transient from 24 volts, 4.5 amps. Okay. No surprise, nice and clean. Just because it's totally underappreciated and often forgotten, for the constant current mode, the current switch on transient. And yeah, I'm probing here across a 0.1 ohm series resistor. Let's see. Interesting, huh? That's absolutely terrible. Look at that. So from here to here, 400 millivolts, that's 4 amps, yeah, our target current. And we're overshooting here 300 millivolts, so 3 amps. And the whole thing is over within timescale 10 milliseconds, so 20 milliseconds. So at high loads, don't switch the output on and off with when in constant current mode. And now I'm forced to do a measurement on on a lower current, if that is also so bad. Let's try the same with 500 milliamps. And yeah, this is my third attempt at capturing it because, you see, single mode and go. Oh. So that's 500 milliamps here, and that overshoot is 1 to 3 amps. Yeah, in a duration of 10 milliseconds. No. Let's try that a little bit different. The output is on, but I'm at a current limit of 1 milliamp. And now I will turn that up to 500 milliamp. I have to go to single capture here. So 1, 2, 3, 4, 5. And oh, that looks much better. Same scale as before, but now it takes it 50 milliseconds to ramp up. And nice ramp up, absolutely smooth, no overshoot. So that's the way to go. Do not use the output on off with constant current mode. There are 2 more transients we have to have a look at, and that is the switch off for overcurrent protection and overvoltage protection. Since I've already set up the whole thing for current measurement, I set the overcurrent protection at 4 amps. And if I switch on, we are drawing 3.5 amps, and 1 row of halogen bulbs is off. I go to single mode and then I switch them on, and that looks absolutely okay. Well, Let's try that with over voltage protection. Okay, last transient, over voltage protection, and we're currently drawing about 40 watts, and as you can hear, the fan is annoyingly loud, even at 40 watts. Anyway, over voltage protection is set at 12 volts, if you can read that. And we're currently at 11.5 volts, 3.6 amps constant current. And if I now switch off some lamps or switch them over to 24 volts, yeah, we get overcurrent protection and the transient looks perfect. This year is really not off to a good start. I have that display problem here again, and maybe it's a loose connection. I don't know. Sometimes, yeah. Or last time when I filmed it, it fixed itself, but no. This time, obviously not. And just by the way, the unit is still fully functional, so yeah, it beeps and you can switch the output on and off. It's there, but the display is dead as a dodo. So I guess maybe it's just a loose connection. Anyway, maybe we do the teardown right now. Anyway, there are just 4 screws on each side and there's no guarantee sticker, so we should be able to open that up without a problem and have a peek. Okay, if I'm right, I should be able to, and I'm not. So, my question is, maybe the top screws are also important in the grand scheme here. Okay, but now it's quite easy to lift that up. And yeah, let's first see where the fault could be. Yeah, this is obviously here. Let me try to give you a better view. Yeah, that flat flex is obviously going through to the LCD. On the other side, I can't see anything wrong with it. Looks quite good. I fumble around with it for a while and see if I can, yeah, reanimate the display. I got the flat flex out and reinserted it, and now I cycled it, yeah, about 20 times, and now the display seems to be back again. So yeah, probably just a loose connection due to the transport or something. I don't know, or some oxidation, yeah, from riding in a container ship over the big seas, yeah, the salty air, who knows. Anyway, yeah, I put it together again, and then we'll continue. Okay, I was just setting up everything again, and yeah, the display is dead. It's still working, but it's just, yeah, the display. Okay, once again. I do hate these kinds of failures. Anyway, yeah, front plate, to get that off, we need to loosen these 2 screws. And 2 screws at the bottom. And it helps if you lift it up a little bit so it's not sitting here on the front plate. And I screwed in all 4 screws again, because you have absolutely no chance to move that even, half a centimeter away without snipping through all the zip ties here and degunking the connectors. So I will close it up after this video and send it in for repair or replacement. Anyway, because it's already open, we can have a little look-see. That was initially planned for part 2. A quick overview: we have here this big transformer, okay, and front with all the intelligence, we already seen that. Other big features here, caution, 71 volt, 12,000 microfarad filter capacitor. We will have a closer look at the power board in a second. AC input here, we have a close look at that, and the RS232 daughter board. On the other side, we see again that big old transformer here, the heat sink, which is quite small for my taste. The cooling fan, again the mains AC input board, and that's it. The control board and the board that holds all the front connectors. There are really no surprises here on the control board. That up here with these drivers, I guess that's the LCD controller. So maybe something's wrong with the LCD controller. I don't know. A little microprocessor here for controlling. The rest is probably analog to digital, digital to analog converters, and maybe some op amps and the piezo beeper. Controller board from the other side. Here's the LCD controller again, and on the other side the flat flags to the LCD, again the controller. Here we have a little bit of a power supply unit, and this comes directly, I guess, 6, 7, 8 volts AC from the transformer. It also has a mains earth connection. I don't know why. And this whole bundle of cable goes back to the power board. So I guess here the current signal and control signals go to the back. This here is connected, we'll see that in a second, to the board that's holding all the binding posts. I guess here the output voltage measurement happens. Here's the board for the binding post. This goes back to the power board. This is where the power comes from, to the binding posts. It also has there in the back connection to mains earth, and that cable, we saw that this goes to the control board and gives you the output voltage. There's a rather large output, electrolytic output capacitor there. I can't read the value, sorry, and a smaller ceramic one right behind it, right there. You can see this, the half moon. Then we already saw that in the overview, the RS232 daughter board, that flat flex goes to the front. And here is the power board, and this is one big shunt here. Okay, these are not 4 shunts, this is one big shunt. Some, I don't know, driver transistor and stuff here. The big filter capacitor, caution, 71 volts, 12,000 microfarads. We already saw that. And what you can also see there in the back, I tried to zoom in a little bit more. Sorry, it's a little bit grainy, the picture, because it's dark inside there, but you have here at the bottom 2 big power transistors, and that's here a full bridge rectifier. The mains AC input board has the usual filtering, common mode choke, filter capacitor, more for protection against voltage spikes, and well, there's something else on the other side. And by the way, these 2 wires, they go to the front, to the real mains AC switch. On the other side of the mains AC board is, yeah, we saw the filter capacitor, a big old power resistor. And yeah, these leads, they go to the transformer. And then there is a Panasonic relay on it. And this is obviously driven from the power board. That connector goes down for the to the power board. I don't understand it because, yeah, this goes to the transformer primary. So if that relay is switching off the transformer primary, then you have no supply voltage to do anything. So the only thing that comes to mind is that this is an somehow an emergency shut off. So the power board can signal the relay to open, and then mains AC is cut, but then all power is lost to the unit. All in all, it's, yeah, the insides, they look okay. It's all a little bit cramped. I mean, you have a solid transformer here, that's a plus. The only thing, yeah, because they try to squeeze it in such a small form factor, the heatsink. The heatsink is relatively small, and therefore you need a high RPM fan to get enough airflow through it to transport the heat away. And yeah, you heard it. The fan is really, really annoyingly loud under load. Yeah, even if you just draw 50 watts out of that thing. Yeah, one last remark. There are actually, yeah, I guess one base tab and 3 different tabs coming out of the transformer. And there are 2 relays, we saw them from the other side, I guess, on the power board to switch between the 3 different output tabs of the transformer. But that's it. So, an unexpected end to this video, as I said. 2021, probably not gonna be my year, huh? Let's see, things will look up from here on, I'm sure. Just, yeah, out of interest, if I switch it on now, the display is back. I hate these kinds of failures. But anyway, I will monitor that. Maybe it's a thermal thing, or some chip is not quite what it should be. I will just time it and see how long it takes until the display fades and goes away, and document it, and yeah, send it back for repair or replacement or whatever. I will keep you in the loop how that turns out. Yeah, until next time, bye.